Okay, so I will go through M16 quickly here, and I'm going to use my idea again, so the ordering of the questions is slightly different. So the first question is still the mixed Reordering question, so let's derive the best response function very quickly and get to the diagram. So first we need to figure out the best response of, say, the role player, and it should be a function of the action of the column player, so it should be a function of Q, and we're going to write this in terms of P. Let's call it P star. So we will say the probability of playing U for the column player is, for the role player is P, and playing D is 1 minus P. And similarly, the probability of playing L is Q and 1 minus Q for the column player. So we derive the best response by considering the case when U is strictly preferred to D. So if I play U, for the role player, if I play U, then I would get 7 was probably Q and 0 was probably 1 minus Q. So I'll just write 7Q here. And if I play D, I will get 7 was probably Q and 7 was probably 1 minus Q. So I will always get 7 basically. So that means if we solve this, then its Q is larger than 1, which never happens. So we only want to divide it into two cases, when Q is equal to 1 and Q is less than 1. So if Q is less than 1, then 7Q is less than 7. So D is actually preferred. So I will always be playing D, and that means P would be 0, because P is the probability of playing U. So, and similarly, when Q is 1, then it means they are equal, so I don't care. So I can mix any way I like. So any number between 0 and 1 will be okay. And Q is 1 corresponds to the case where the column player is always playing L. So when the column player is always playing L, then I don't care. I can mix any way I like between U and D. So that's that blue part. And otherwise, I'm always going to play D. So that's why I have this blue line here. So that's how I get one of the best responses. And similarly, we can consider the best response of the column player, which is a function of P, and we write it as what Q value we get as the best response. So we do exactly the same thing, and we consider when we prefer L to R. So if I play L, I will get 0 and 6. I will get 0 with probability P, and 6 with probably 1 minus P. And if I play R, I'll get either 4 or 0, so I'll get 4 with probability P, and 0 with probability 1 minus P. So we can solve this, and this is P is less than 0.6. Yeah. So when P is less than 0.6, I'm going to prefer L. So preferring L means I'm going to play Q is 1. And if P is larger than 0.6, I'm going to prefer R, which means Q is 0. And in between, I don't care, because I get the same payoff from L and R, so I can mix any way I want. So that means when P is less than, P is the probability of playing U. So when P is less than 0.6, so this point is 0.6. When P is less than 0.6, I'm going to play L. So this is why we have this region here. And when P is larger than 0.6, in that region, I'm going to play R. So this corresponds to R. That's this region. And in between, I don't care. So that's how we get the best responses. And by definition, the Nash equilibria are just the region, are just the points where we have mutual best responses. So P is the best response to Q, and Q is the best response to P. So that's this region highlighted by green. And that will be the Nash equilibria, and it corresponds to P from 0 to 0.6. That's why the answer is 0 to 0.6. Okay, so moving on to the next question. I'll actually talk about this next week, so I'll skip it here. And the third question is similar to the vaccination question from I think 15. And the only difference is we have a different story, and also we have costs here, and the firms are minimizing the cost. So there is a reversal in the inequalities, but everything else is exactly the same. So we divide into two groups. One group of people are these N firms, N players who are choosing the action R. So basically the firms who are releasing pollution into the river, and in equilibrium, because they picked R, that implies the cost from R should be less than the cost from F. So for these N players, N firms actually, who picked R in equilibrium, the cost from R to these people must be smaller or equal to the cost from F, because that's why they picked R, right? So then we just need to compute the costs. So the cost from R is, the coefficient is large, so there's large cost with the pollution. And in comparison, if they install the filter, which costs like 90 units, probably not $90, we should have something like this. But the problem is the N firm is in equilibrium, they are picking R. So if they switch, there are no longer N firms. So we actually have one less firm polluting. So that's why the value N here is decreased by 1, and we still have the cost of installing the filters. The reason why we have -1 is just like in the vaccination problem, I'm going to call it me. That's my company. My company switched from releasing the pollution to not polluting. So the total number of people polluting the river is decreased by 1 and decreased by basically my company. So next, for the remaining 16 minus N firms, in equilibrium, they are picking F. The justification must be the cost from F for these 16 minus N firms must be smaller than the cost of releasing the pollution. So if that's the case, then the cost of F is the same, 3N plus 90, should be less than or equal to 15. I'm adding 1 because I am the firm who choose to from not releasing to releasing. So there's one more firm, that's me, that is polluting the river. So because, again, I'll say me, and I'm switching from F to R. So now we have two set of inequalities. Actually, there are only two. And then we can solve them. We can combine them and solve them. We'll get something like n is between two numbers. And it's unlikely that these two numbers will be integers. In case they are not integers, there should be only one number in between those two numbers. And in our case, it's 7. Okay, so the next question is a friendship link question, and it's still asking about the luckiest case. So let's draw the diagram. So person A has 5 friends, and each one of the friends has 5 friends. So there are 4 links away from, at this level, one of them is Bob. And in the luckiest case, Bob is the first one that we'll search at level 4. In the worst case, Bob is the last one, so that's the worst case. So here we are talking about the luckiest case, and we're also talking about BFS. So in the luckiest case, B is the first person we search at level 4, and for BFS, we need to search everything in levels 1, 0, 1 to 3. So we need to add up all of these nodes, the number of them plus 1. So the root plus the first level plus the second level, because each of the 5 friends has 5 friends, and third level, and then add that one is B here. So that's how many people we need to search. So the next question is the highway question. It's actually very similar to the vaccination and the pollution question we did earlier. So I will not set this up the same way. We can actually write down the inequalities, but here we actually can solve for an integer. So I'll solve for the integer directly. So the reason behind this is the amount of time it takes to go through the long way and the direct way should be the same. If it's not the same, then we will have, so for example, if the long way takes longer, then some of these people will switch to the direct way. And if the direct way takes longer because there are too many people taking it, then some of them will switch to go through the long way, which will take less time. So in equilibrium, we should have the amount of time it takes to go through the direct way and the long way should be the same. So we'll just set this up, and it turns out we can actually solve it to be an integer. So in the vaccination and the pollution case, if we set up the equation that way, most likely we will not be able to get an integer. That's why we set up two sets of inequalities. Here, if we set them up, it will just be n divided by c. C is 16. Is equal to 1 hour. So we directly know that n is 16. So in equilibrium, there will be 16 people taking the direct way. And the question is asking about how many people are taking the long way. So the total number of people subtracting the people taking the direct way. So that's the answer here. Okay, so the next one, the battle of the sexist game. And the difference between this and the same question from M15 is here we're asking about the role player's expected value. So what I'm going to do is just set the value from the role player Romeo playing B equal to the role player playing S. So and both of them in equilibrium should be the value of the role player in a Nash equilibrium. So in order to set them equal to each other, we need the probability, we need the action of the column player. So we'll say Juliet will play B with probability Q and S with probability 1 minus Q. So then if Romeo plays B, then he gets 4 with probability Q and 0 with probability 1 minus Q. So these two numbers. And I'll set it equal to getting 0 with probability Q and 3 with probability 1 minus Q. So we can just solve this. This is just Q is 3 over 7. And we can just plug in 3 over 7 back into this equality. On the left-hand side, we're going to get 12 over 7. On the right-hand side, we'll also get 12 over 7. Well, it proves we're right. I mean, they're equal. And both of these are the values of the role player in the Nash equilibrium. Okay. So the next question is the local search question. So there are two ways of solving this. One is by just looking at it and basically guess which one will flip the most number of edges, basically. And that may not always work. So the long way to make sure that you are right is just try to flip everything and see which one decreased the cost by the largest. And that's also how I coded the autograder to do. So we will go through a few and then I'll make a guess and hopefully that guess is correct. So if we flip the first one, so the question here is we want to minimize the number of edges connecting two nodes with the same color. So we basically want to maximize the number of edges that has different labels. So here, for example, if we have plus here, then the score of this edge is, both of them are plus, so the score is 1, and here the score is 0. And if we flip this plus to a minus, then the score between these two will be a 0, and these two will be a 1. So the score is unchanged. if we flip node 0. So we'll continue this process. And originally, if we look at node 1, then this edge is 0, this edge is 1, same color is 1, different color is 0. So this edge is 1. If we flip, then we are changing this to a plus. Let's use a different color. We're changing this to plus, so this will be 1, and this will be a 0, and this will be a 0. So the sum of these three is 1, and the original sum is 2, so the score decreased by 1. So the score decreased by 1 if we flip 1. So we can probably go through all of them, but let's guess probably this one is the best one. So I'm going to flip this to plus. So originally the costs are 1, 1, and 1. If we flip to plus, it becomes 0, 0, and 0. So the score would decrease by 3 if we flip 7. So you can try all the other ones. None of them would decrease the score by more than 3. So the answer is 7. Okay. So the next question is, there are no go states, and we're doing DFS. Actually, it doesn't matter whether we're doing BFS or DFS. We need to search everything because there are no go states. So we just need to compute how many nodes are there in the whole tree, then we're done. Right? So there are 4 levels, and each one contains 3 nodes. So we have in the first level, in the zeros level, the root, there's 1. And in the first level, there are 3. And in the next level, 3 squared. The third level, 3 cubed. And there are 4 levels in total, so 3 to the power 4. So that's basically the total number of nodes. And since there are no go nodes, we need to check everything. So that's why the answer is just the total number of nodes. The next question is another question that will be on the final exam, and it's actually similar to the KN question from the midterm. So it's similar to like finding the midpoint between 2 key points, because the midpoint means if we move to the left by a bit, it's closer to 1 point. If we move to the right by a bit, then it's closer to the other point. So the idea behind this is the same. So let's write this down. The points are -7, -5, and 0, 3, and 7. And one cluster C2 is -11. So we want to figure out where should we place something like C1 here, so that all 5 points belongs to C1 and C2 is empty. So the key point is probably you should notice it's -9. So if -9 belongs to C1, then every other point will belong to C1. So we want to find C1 such that if we move -9 a little bit to the left, it will be closer to C1. If we move to the little bit right, it belongs to C2. So by definition, that's the midpoint between C1 and C2. So, and if the distances are equal, note that there is the tie-breaking rule that says in case of a tie, then it belongs to C1. So that's exactly what we want. So that's why we set -9 as the midpoint between C1 and C2, and C2 is -11, so we can solve for C1, and the answer is -7. Okay. So the next question is called the volunteer's dilemma, and I went through this question in the pre-recorded lecture, but I did not have time to go through this during the actual lecture. We'll actually play this game sometimes next week. But in any case, let's solve this. And I think we have already solved many mixed strategy Nash equilibrium problems. And the strategy or the approach that we use is always setting the expected payoff, expected value from one action equal to the other one. And at that time, people will mix because people, the players will be indifferent between the two actions. So any mixing probability will be the best response. So that's how we will solve this problem as well. So the reason why they use the mix strategy and they mix the same way, so let's assume they mix it by, say, probability P of calling the police and probability P, y minus P of not calling. And the reason they mix is because the expected value or expected cost of calling is actually equal to the expected cost of not calling. So in an equilibrium, again, in an equilibrium, the reason why someone would mix is only because that person is indifferent. If that person prefers, if the cost of calling is slightly lower, then I would not mix. I would just play C for sure. So that's why the only reason why they would mix is when these two things are equal. And let's compute the cost. So the cost of calling is 1. And the benefit, actually here we are not computing the cost, we're computing the value. And the benefit from calling the police is 5. So hopefully the police will come and solve the problem. Then everyone would get a benefit of 5. And I am one of the maybe few people who are planning to call. So I'm going to incur a cost of, say, picking up the phone and actually dial 911. Then that cost will be 1. So my net benefit or value will be 5 minus 1 if I call. So note that this does not really depend on what the actions, what the other players are doing. Because if I choose to call, there only needs to be one person calling the police. So if I'm the one, then I will get the benefit for sure, and then I'll incur the cost. However, if I choose not to call, then my benefit actually depends on what the other players are doing. Right, so I will get the benefit. I'll basically free ride if someone else called the police, and if no one else called, then I will not get the benefit. So my 5 really depends on the probability of at least one other player. So at least one of the other 7 players called the police. And then I won't incur cost, so I don't have this minus 1 here. That's basically my value. So the problem here is just computing what this probability is. So let's see. The probability of at least one person calling is just 1 minus the probability of no one else called. So no one called. So that's easier to compute. That's just 1 minus one person not calling to the power 7. There are 7 other players, not excluding me. So because I am already one player who is not calling in this situation. So I'm definitely not calling. So I'm depending on one of the 7 other people calling. Okay. So now we have an expression like this. Then we can solve for P. And P is 5 minus 1 divided by 5. And we need 1 minus this. And we need to the power 1 over 7. And we need 1 minus that. So that's basically P. And P is the probability that one player is calling. And the question is asking what's the probability that no one called. So it's basically, the question is asking 1 minus P to the power 8. That's the probability of one person not calling. That's the probability of all 8 players not calling. So that gets simplified to just this part inside to the power 8. So that's this expression here. Okay, so that's the volunteer's dilemma game. And the next one is the game with chance. So if you know the diagram, then you can just highlight on the diagram. So the max of these two is, so we go from the bottom of the tree, go back to the top of the tree. So here the max player is deciding, and the max player will pick 3 and pick 3 here as well. And then we have the max player here picking 7, and the max player here is picking -3. So next, the chance is randomizing, so I need to compare the expected value. For the mean player, I'm comparing the expected value between 3 with probability 0.05 and 3 with probability 0.95. That's 3 for sure. And here is 7 with probability 0.32 minus 3 with probability 0.68. So I guess this number should be slightly smaller than 3. And you can try to compute this. If it's larger than 3, then the answer is 3. If it's smaller than 3, which should be the case, then it's just this number. Because the mean player is picking the minimum between these two numbers. Okay. So the next question is the large tree question. And we're doing DFS. And we know the states are 1, 2, 3, 4, 5, 6, 7, and 8, and then you get the pattern 8, the next one is 16, and so on. So eventually you'll get 512, which is 2 to the power 9, is it? So here we're doing DFS. And using the convention, I'm going to search 1, and then we're going to expand 2, and then we're going to expand 8 and 16, and so on. So basically, we expanded 2 to the power 0, 1, 2, 3 until 9. So there are 10 of them, and we're done. So that's why the answer is 10. So if the goal state is, say, 511, then we actually need to go through the whole tree. Then we do 1 plus 2 squared plus 2 cubed until we get like 2 to the power 8. So we need to search everything basically. So then the answer becomes 511. And here, because we're using DFS and 512 is on the leftmost branch, then we search that one first actually, then we're done. Okay, so the next question is the reordering question. And so the first step is always solve the game first. And the mean player is playing, the max player is playing first and mean player next. So picking the minimum, which is this number, the minimum is this, and the minimum is this. And the max player will pick the max among the 3, so the max player will play this. So basically the equilibrium or the solution is the max player choose this and the minimum player choose this. So the first branch must be searched, and also the solution must be searched. So we may as well put the solution as the first branch, and then we can search all 3 of these any way we want because we cannot prune any of them. Say if we search -5 first, we don't know anything about the remaining branches. So we still need to search 5, even though somehow here we know that they are larger. But when we are searching, we don't know. So we need to search these 3 any way we like. So all 3 of them cannot be pruned. And next, we're going to search, say, that branch. And suppose we search this sub-branch first, then it means at this point, the max player is already getting something larger than or equal to -5. Because the max player is maximizing between the first, second, and third branches. And I already get -5 from the first branch. And now I'm seeing -9. And I know this is a mean player. So the mean player is going to minimize, so the main player will get something that's at least -9, which means it's something less than -9. So for the max player, I already know that I can get -5. Why do I care? Like anything less than -9. So I'm going to prune these two. So to think about if you use a different ordering. So for example, if you search 7 first, then I only know that the main player will get something less than 7. So it's still, there is kind of possibility for the max player to get something larger. So the max player is still interested in keep searching and see if we can get something like maybe 6, then still larger than -5. It turns out no, but the max player and both the max player and the main player are still interested in the remaining branches, so we cannot prune anything. So that's why we will search this -9 branch first, then the max player will be no longer interested in searching the remaining branches, and 7 can be pruned. So you can probably guess what will happen next. So I'm going to search -10 first. Somehow my pen is not working, sorry. We'll search -10 first, and so the main player knows that he or she will get something less than -10, so the max player will no longer be interested in searching the remaining stuff. So at this point, we pruned 4 nodes. Okay. So moving on to the last question. So the correct way of solving this is actually compare all actions, say compare 1, 2, 1, 3, and so on, so to see which column is dominated and which row is dominated. But one trick to do this is because all rationalizable actions, I actually said it wrong, all Nash equilibria must be rationalizable. So if we find the Nash equilibria, and if there's only one, then that one must be rationalizable. And so we will go that, we'll use that approach first, and then we'll figure out if we just eliminate those dominated actions, we'll get the same thing. So to figure out the Nash equilibrium, we need to figure out the best responses. So if the column player is playing 1, then the row player is best responding by picking 3, action 2, and best response, basically the largest number of each column. And for the row player, if the column player, if the row player is playing 1, then I'm picking also the largest number, because everyone is maximizing the largest number among each row. So this is 1, and this is 0, and 2, and 1. So there's only one. That's mutual best response. So that's only that's the only Nash equilibrium. So one problem is we are assuming there is only one rationalizable action, so which may not be the case. So we should still try to just remove the dominant strategies. But if we have these best responses, then I guess it's easier to find which ones are dominated, because sometimes action 1 and action 2, they are best responses, so they will never be dominated. So that's why we only need to look at 3 and 4. So if we compare 3 and compare, say, row 1, then -3 is less than 2, -2 is less than 0, 2 is less than 3, -2 is less than 7. So 3 is dominated by 1. And when I say dominated, it means strictly dominated. So basically, no matter what the other player is doing, playing 3 is always worse than playing 1. So we can actually see the same thing is happening with action 4. So that one is also dominated by 1. So when we are iteratively eliminating stuff, we can eliminate these two rows. So it actually doesn't matter if we eliminate the rows first or the column first. So you can do either. And now let's try to eliminate the columns. So we should highlight the remaining columns. I get 1, 0 from 1, minus 3 from 2, minus 1, minus 5 from 3, and minus 2, minus 5 from 4. So I guess the choice is obvious, right? 1, 0 dominates everything else. So all three of them are dominated by 1. So for the column player, I'm just going to remove all three of these actions. And now we will have the row player comparing. So row player comparing 2 and 1, 2 is actually better than 1, because if I play 2, I'll get 3. If I play 1, I'll get 2. So 1 is eliminated. So the only one left is also the same as the Nash equilibrium, which is 3 and 0.